In this video, we'll be seeing how to find out whether a course schedule is possible to be completed or not. Before jumping into the solution aspect, let us try to understand the problem statement. We'll be given the number of courses that need to be completed. Let's say number of courses is 2. We will also receive a prerequisites array which will be having values that represent the blocking codes for a specific course. For instance, for course 1 to be completed, a prerequisite is that course 0 has to be completed. Without completing course 0, you cannot do course 1. And the aim is that we have to find out whether ultimately it is possible to take all the courses or not. And if you can finish all the courses, then we have to return true from our outcome. Otherwise, we have to return false. And we will be building a solution using depth first search traversal into a graph. Now, we have received the values in the form of these prerequisites and the number of courses. How do we build a graph out of this? That is the first question. And secondly, we will be doing this depth first search traversal to see whether or not the courses can be completed or not, and how we will figure out whether the courses will be completed or not. In this case, we have course 1 being dependent on course 0. So this goes to this one. So in this case, we can see 0 doesn't have any dependency. So 0 can be done independently of any other course, and course 1 needs 0 to be completed before you can take course 1. And this is just a one directed graph, and we can say that course can be completed. First you will do course 0 and then you will do course 1. In another example that we see here, what we look at is that there is course 0. So you have course 0. Then this course 0 is going to be a dependency for course of 1. So you have to complete course 0 first for course 1 to be completed. So similarly, it will be something like this. So you have to first do 0, then you do 1. Then you have course 2, which has a dependency on course 1. So for doing course 2, you have to first do course 1. And then for doing course 0, there's a dependency on course of 2. And this is going to go back to 0. And you can see here that you will try to do course 1. For that, you will try to do course 0. Then you will say you want to do course 0, but to do course 0, you need course 2 be done. But for course 2 be done, there is course 1, which is again dependent on course 0. So this forms a cycle of dependencies, and because of this cycle being present, you cannot really complete all the courses because this creates a deadlock. So the aim here is first build a graph which is looking something like this or this, and then see if there is a cycle or not. In the first case, there was no cycle. You could just go in this direction from 1 to 0, and we had this adjacency list here that was formed, based on which we tried to make sure we check whether there is a cycle or not. And in the second case, there was a cycle, so you could not complete the courses. And this is the basic mechanism. The first step, wherein you create this adjacency list as step 1, and step 2 is then you traverse this graph, which is the representation via the adjacency list, and then you see whether cycle exists or not. Let's first do the first part before jumping to the second aspect of doing a depth first search. The first part is just building this adjacency list, and to build the adjacency list, we can simply follow this process, wherein I will just say create a graph. In this graph, I will first initialize the number of courses that we need to do to an empty adjacency list association, and that will look something like this. I will just say for let I is equal to 0, I is less than the number of courses that are supposed to be taken, I plus plus, and then graph of I is going to be just having an empty association. After this, I will say for let course comma pre-course of the prerequisites that we have received. The prerequisites is going to be an array of all the dependencies that we have for a specific course, and I will just say graph of a specific course dot push the pre-course that exists. And this way we complete our step 1 of having a dependency based adjacency list. And this is the graphical representation wherein the graph is represented as a adjacency list to work with. And with this adjacency list, now we will be doing a depth first search. And how the depth first search mechanism is going to work is basically we're just going to go from node to node and do something like this. We will be having a tracker called as visited. So I will say for the second example that we are looking at, wherein there is a cycle, I will keep a tracker which says visited, and I have 3 courses, course 0, course 1 and course 2. So for all 3 I will have a representation here, so 0, 1, 2. Initially visited is going to be false, and I will be also keeping track of the DFS traversal that I do in a specific sequence. What I mean by that is, what is our main aim here? The aim here is to find a cycle. And when can we say that there is a cycle? You start from a node, you go to the dependency nodes that you have, and then you see for that specific dependency node that you have, is there any other dependency? And if during the dependency you see that a specific node is repeating itself, in this case this was the node that is repeating itself while doing a depth first search traversal. You went to this, you said you have 0 which you had already visited, and then you see 2, and then you again see 0 when you come back in this cycle. So if something is repeating during a DFS traversal, so you keep on going down to all the children in a specific node, and the children in this case are basically the dependencies in this prerequisites that we form in the adjacency list. And if any node repeats itself during this traversal, that would mean that a cycle exists. Now we will also keep this DFS visited stack, wherein I will initialize it to false for all the courses that we have. And why do we have 2? Why do we have visited and why do we have DFS visited stack? Because this is for the current depth first search recursive call, how deep you can go, and this is if you have already visited, you no longer need to consider it, just move on to the next one. So we will first start with 0, and in this case first we are going to be building a adjacency list. Let's work. So for 0, 1 and 2, let's see what are the dependencies. For course 0 that we have, we need to first complete course 2. So for 0, 2 needs to be completed. For 1, we first need to complete 0. So for 1, we need to complete 0. And for 0, first we need to complete 2. And for 2, we first need to complete 1. So this is the adjacency list that we have with us. Let's go from the 0th one. We said that for the 0th one that we have, initially visited is false. I will say check whether we have DFS visited stack entry for it. 0 doesn't have any entry for it, so we will just proceed ahead. If there is an entry, that means you have found a cycle, and you will just exit and say the courses cannot be completed. So the aim here is to find a cycle, and this stack is going to be tracking if there are any repetitions within this specific course. If there is already a visited flag here, that means the course is going to go in a cycle. Now for 0, we will say we have visited it initially, and because the thing is marked as true here for 0, it is still false, we just proceed. For 0, we see 2 is its a pre-course dependency. Then I will say for 2 that we have with us, is 2 having an entry in the stack? 2 is also not having any entry in the stack. So I will first mark 2 as visited because it's a dependency and we are going into a depth first search. So first we do a DFS with this, then we go into DFS of its dependency, which is going to be 2. And then we will say that for 2, what are its dependencies? And before going into the dependency trigger, another important step is, as soon as you visit a 0, you marked it as visited, then you're going to go to its pre-courses, which is going to be 2. Just before doing that, I will mark my 0 as true in the current sequence, and so that whatever children it has as its dependencies, I will keep going through them while making sure that this is still true. So then I go to 2, I mark 2 as visited, so I will say for 2, this is going to be true now. So for 0 and 2, the flag of visit is true, and we have also marked 2 as visited now, so I will mark it as true in the stack. And then after marking it as true in the stack, I will see what are its dependencies. So for 2, the dependency is 1. I will go to 1 now. For 1, I will see whether is it marked as true. In this stack, it is not marked as true. So I will proceed ahead, wherein I will now mark 1 also as true, which is visited, and then I will see what are dependencies of 1. So for 1, we have dependency as 0. So now, before just going ahead, I will first mark for 1 also in the stack as true. That means I'm trying to go through the pre-courses of this specific node 1. Then for 0, I will say, hey, is 0 already in this stack marked as visited? Yes, it is. If it is marked as visited, that means a cycle detected, and because a cycle has been detected, we just say that no, you cannot complete all the courses. And now let's convert whatever mechanism we covered so far into code. So far we have the adjacency list created with us. I will just say go from the 0th course that you have with you all the way to the number of courses that are supposed to be completed. You just keep on going into this loop. And now what we will do is, here we will do a depth first search course by course. So I will say if the depth first search for a specific course returns us that there is a cycle, because this DFS is going to return true if there is a cycle. In that case, just return false. That would mean that you cannot complete all the courses. If it is not returning, in the end, the statement is just going to say return true at the end. And now for building this DFS, the depth first search mechanism, we have these 2 trackers. One is visited and one is DFS visited stack. And for that, what we will just say is constant visited is going to be a new array of the number of courses that you have with us. I will just fill them with false initially because we just go through them while we do the DFS and update the values. And one is going to be DFS visited stack. This is going to be keeping track for the current depth first search sequence of a specific node, how in the depth you can go. So you will go to all the children of a specific node, and once you have traversed all the children of a specific node, you just reset this stack sequence. So it's just going to be for the current sequence when you have a specific node with you. And after this, we having the core part of the functionality, wherein we are going to be picking up a node, and this node is going to be returning us whether a cycle exists or not. So let's say by default no cycle exists. If in this DFS visited stack for that specific node, if there is an entry, then we will say return true. This will be an indicator that a cycle has been detected, and that is the core part of the logic. If a cycle has been visited, or if you have already visited it, then you can just return. You don't have to do the process of going through its pre-courses. because you have already visited it once. Then you mark the visited for a specific node as true. You mark it as checked. Then you mark the DFS visited for the specific node as true also. And towards the end, so once all the children have been visited, you reset it, because then you have to go to the next node, next sibling in the pre-course array, and then do the same process again. That's why it says depth first search. You go all the way down, and then from that specific node you backtrack. And once you have gone through all the children, you will just return false. Now comes the part of going through all the children. What do we mean by going through all the children? So for let next of graph of this specific node. So this is going to give us all the pre-courses that needs to be completed for a specific node that exists in this map of ours. And we will say this next. So if the next node, we are going to do a DFS on this next node also. So if we are going to go into a recursive call now, and if DFS of next is going to return us true, then you just return true. And this will go all the children. So it will go from something like this. You will go to 0, then it's going to 2, 1, and then 1 goes again to 0 here. And if the children itself repeats in this DFS stack, then you're going to be returning true from there. And that's pretty much it in terms of the logic aspect that we have. First, we will just make sure that we set the visited as true, we set the DFS visited as true, and once we have gone through all the children, we will just reset the flag again for the next sibling to proceed with. And in terms of the time complexity that is going to be involved here to build the adjacency list, that is going to be big O of m in terms of time complexity. Then we are going to do a depth first search mechanism here, wherein you go through all the children that we have. And similarly, this is also going to be the time complexity here involved as big O of m, because we are going through all the number of courses that we have. Then we do DFS, and when we do DFS, we are going to again go through all the prerequisites nodes that are going to be existing. So this is going to be a time complexity of big O of n. And because we are having time complexity of big O of m here and big O of m here also, and then this is going to be big O of n representation, then the overall time complexity that is going to be involved here is going to be this plus this, because inside this then we are going to do DFS. So the overall time complexity that is going to be existing here is going to be big O of m plus n, because this and this comes into play. You will say that initially we do this, so it's going to be something like big O of m plus big O of m plus n, and we also go through these prerequisites that we have associated with us here, and going through the prerequisites is going to be big O of n. But because big O of m is there, and we also have big O of n, which is going to be going through all the prerequisites that we have. Similarly, the prerequisites are being traced here within this loop that we have here with us within DFS, because the correct position to represent this is going to be just above this, because then it's going to go through all the prerequisites that are going to be associated. So big O of m here, big O of n here, then this is also again big O of m, and then within this we have big O of n. So it's going to be m plus n plus big O of m plus n. This being the major aspect contributing to the time complexity, we can then just say that the final time complexity is just going to be big O of m plus n. And in terms of space complexity that we have with us, that is also going to be big O of m plus n. Reason being that we are first storing here in the visited tracker the time complexity and the space complexity as big O of n, because we are just going to go through all the number of courses, or let's just represent it as big O of m here. Then we are going to keep on iterating within these prerequisites and keep on pushing the data of prerequisites. So for this one, the space complexity, let's say big O of n. So this one has big O of n, this one has big O of m. So the overall space complexity will be big O of m plus big O of n.